Assalamualaikum and greetings everyone. Today's topic is on surface integral of a vector field. Okay, the surface integral of a vector field F measures the flow of the vector field F spreading on a surface sigma in the direction of the outward unit normal vector n from surface sigma, and it is called flux of F, denoted by F dot unit normal vector integrate over surface sigma. So flux of F here measures the flow of the vector field when it goes through the surface sigma. So we want to measure the flow of the vector field F spreading across the surface sigma, and it is equal to F dot unit normal vector integrate over surface sigma. Okay, now let's see how we can evaluate this. In the previous video, I've shown you that surface sigma here, when you write it as a function phi xyz, then the gradient of phi or del of phi is equal to the normal vector to the surface. So the gradient of phi or del of phi is equal to the normal vector. Normal vector divided by its magnitude is what we call the unit normal vector, and the relationship between ds and dA is ds is equal to the magnitude of the normal vector dA. I've explained this in the previous video. Okay, so from here we can write flux of F as F dot unit normal vector n integrate over surface sigma by projecting this onto a region R, which is going to be either on the xy plane, xz plane, or yz plane. Okay, let me explain how we do this again. So F dot unit normal vector ds is equal to, well, we know that unit normal vector is really normal vector divided by its magnitude, and dA is magnitude of normal vector dA, and from here when we simplify this, then we get this is F dot normal vector dA. Okay, that's how we get this formula here. So this is what we're gonna evaluate. That is how we measure flux of F. Okay. Now, on which plane should we project our surface sigma onto depends on how your surface is given. Okay, let's see here. Oops. If your surface is given as z as a function of x and y, what you do is you project your surface sigma onto the xy plane. And of course, unit normal vector ds will be replaced by normal vector dA. But if your surface is given as y as a function of x and z, you project your surface sigma onto the xz plane. And again, normal vector ds, unit normal vector ds will be replaced by normal vector dA. And lastly, if your surface sigma is given as x as a function of y and z, you project your surface sigma onto the yz plane. And again, unit normal vector ds will be replaced by normal vector dA. Okay, so first step is you have to get your gradient of phi, because the gradient of phi, as you know, is the normal vector to the surface. Okay, so first step you need to do is you need to rearrange your surface. So if your surface is given as z as a function of x and y, you rearrange your surface as phi of xyz, which is equal to z minus fxy. And excuse me. And if your surface is given as y as a function of x and z, again rearrange your equation so that you have a function phi xyz, which is in this case equal to y minus fxz. And if your surface is given as x equals fyz, again rearrange the equation so that you have your surface sigma as a function in terms of x, y, and z. In this case, it's x minus fyz. Okay, once you rearrange your surface sigma phi, then you can get del phi, which is the normal vector to the surface. But for every surface, you have two normal vector. Okay, one, and they are pointing in the opposite direction. So let's say, for example, you have this surface, like so. Okay, so this surface have two normal vector, and they are in the opposite direction. So let's say one is pointing this way, okay, and the other is pointing in the opposite direction, which is this way. Alright, so they are both normal vector to the surface. It's just that you need to know which normal vector to choose, because what you want is the outward normal vector. Okay, because the flux depends on the outward normal vector. So we need to pick which normal vector to choose, either this one or this one. Okay, because they are in the opposite direction. Okay, so then we must choose the outward normal vector of phi from del phi or from negative del phi. Remember, they are in the opposite direction. Okay, so we must choose whether to pick del phi, the gradient of phi, or negative gradient of phi to be our normal vector. Okay, so now I'm going to explain which normal vector, which del phi to choose regarding our normal vector. Okay, so here we have 1, 2, 3 cases. Now let's look at the first case. Okay, for the first case, for sigma given by z equals f of xy, the surface is facing either the positive side of z-axis or its negative side. Hence, we should check the z component or the vector unit k of del phi. It is positive k or negative k that makes del phi pointing outwards. So we must choose between n equals del phi or n equals negative del phi. So here, when your surface is given z as a function of x and y, you have to check for the z component. Okay, so the z component there will determine whether you want it to be negative z component or positive z component, because your surface is either facing the positive z-axis or the negative z-axis. Okay, let me explain furthermore. Okay, let's say your surface is given as z equals f of xy. So for example, z is equal to negative x squared plus y squared. Okay, so z equals negative x squared minus y squared, as you know from before. This is a paraboloid where if y is 0, you have a parabola, the set parabola, and if y is x is 0, again you have a parabola that open downwards. So what you have is something like this. Okay, so this would be your surface, z equals f of xy. As you can see, that paraboloid is facing the positive z-axis. So this is facing the positive z-axis. So if it's facing the positive z-axis, the normal vector, the outward normal vector, would be like so. Okay, this would be the outward normal vector. It's facing the positive z-axis. So for the positive z-axis, the z component is always positive, but the x and the y component would be negative. So in this case, you want your k component to be positive. Why? Because it is facing the positive z-axis. The z and the y, the x and the y component varies, because here the x and y would be positive, but if you take this normal vector at this point, the y component would be negative, even though the x component is positive. But the k component, the z component, is always positive. Okay, so first we're gonna rewrite this as our phi to be z plus x squared plus y squared equals 0. So the gradient of phi would be partial x, partial y, partial z. And this is going to be equal to 2x, 2y, and then 1. Okay? And what we want is, we want our k to be positive, because it's facing the positive z-axis, and it is already positive. Hence, this is our normal vector. So normal vector is equal to 2xi, 2yj plus 1k. Alright, so this is one example. Now, let's say your surface is given as, so another example. Let's say your surface is given as this. Z equals x squared plus y squared. Again, this is a paraboloid. Okay, the bowl shape, like so. Okay, Now, well, it can go up forever. Now you can see that the surface is facing the negative z-axis. It is facing the negative z-axis, which means that if you look at the normal vector to the surface, it would be pointing this way, okay, downwards, like so. Okay, so it's pointing downwards, which means that the z component, which is k, must always be negative. We want it to be negative because it is facing the negative z-axis. The x and the y components varies. In one side it is positive, but on some points it is negative. So the x and the y component varies between positive and negative, but the z component is always negative. So we check for the z component. Okay, so in this case, let me rearrange the equation again. So the surface, I'm gonna rearrange it because our normal vector is either del phi or negative del phi. So rearrange the equation, we would have something like this. Okay, and the gradient of phi is equal to differentiate phi with respect to x, we get this, negative 2y. Differentiate phi with respect to y, we get negative 2y. Differentiate phi with respect to x, we get 1. Okay, but our normal vector should consist of negative z component. We want k to be negative, but here k is positive. So our normal vector would be negative del phi. Okay, so our normal vector would be negative del phi, which is 2xi, 2yj minus 1k. Alright, so this is our normal vector. Alright, so if your surface is given as z as a function of x and y, what you do is you sketch your surface and then you look at your surface whether it is facing the positive z-axis or negative z-axis. If it's pointing towards the positive z-axis, you want the k, the z component, to be positive. But if your surface is facing the negative z-axis, you want your z component to be negative. And then you check your del phi, whether your z component is already the same sign as you want. If it's not, then your normal vector would be negative del phi. So in our case here, we want k to be positive. It is already positive, so your normal vector is del phi. In the second example, we want our k component, z component to be negative. When we check here, the z component is positive. We want it to be negative, so normal vector is negative del phi. Okay, so that is case number 1. Alright, now let's look at case number 2. For case number 2 is when your surface is given as x as a function of y, z. So your surface is going to be either facing the positive side of x-axis or its negative side. So you have to check for the x component, alright, because it's either facing the positive x-axis or the negative side of the x-axis. So you check for the I component, the x component. So if your is it positive I or negative I, depending on your surface. So then you need to choose the correct del phi. So your normal vector is between del phi or negative del phi. You just have to refer to the surface. Okay, let me explain further for case number 2. Okay, so for case number 2, your surface is given as x as a function of y and z. Okay, so it's either facing, so your surface now would either be facing the negative x-axis or positive x-axis. Okay, for example, let's say you have a surface x is equal to y squared plus z squared. Okay, so if you have this is also a paraboloid, but it's going to be a paraboloid like so. Okay, it's a bowl shape as well. That's ugly. Hang on, let me erase that. So it's a bowl shape as well, but it's like so. Now you can see that it is facing the negative x-axis. Okay, so the normal vector would be pointing that way. Okay, so it's pointing, it is facing the negative x-axis, which means you want your x component to be negative because it's facing the negative x-axis. So you want your x component to be negative. Okay, back to our surface here. So now remember we have to rearrange. We have to rearrange the equation for the surface. So rearrange it. So it's going to be this one. Okay, rearrange it. So our phi now would be, you can do it either way you like. So let's say I'm going to rearrange it so that the equation now becomes x minus y squared minus z squared equals 0, and then find del phi, because it's going to be your normal vector is either del phi or negative del phi. Okay, so differentiate phi with respect to x, you get a 1. Differentiate phi with respect to y, you get negative 2y. Differentiate phi with respect to z, you get negative 2z. Okay, now check your x component. This is your x component. It's equal to positive 1. But what we want is negative x component. So then your normal vector would be negative del phi, which in this case would be negative 1, 2y, 2z. Okay, so that would be the normal vector because you want your x component to be negative because the surface is facing the negative x-axis. Alright, now let me give you another example. Let's say now your surface is x is equal to negative y squared minus negative z squared. Again, this is a paraboloid as well, but this shape of paraboloid, it's ugly paraboloid. Oh well, maybe I can sketch it a bit prettier. Oh well, same old, same old. Alright, so now you can see that the surface is facing the positive x-axis. So your normal vector would be like so. Okay, so the x component here will always be facing the negative, the positive x-axis, which means that you want the x component to be positive. Okay, now let's say here we rearrange the equation of the surface so that you have x, y, z function. So you can rewrite it as x plus y squared plus z squared. Then the gradient of phi now would be differentiate phi with respect to x, you get a 1. Differentiate phi with respect to y, you get 2y. Differentiate phi with respect to z, we get 2z. And then check the x component. You want it to be positive. Now you can check the x component. It is positive. So this is your normal vector. Okay. Alright, so your surface is either facing the positive x-axis or negative x-axis. And then you check for the x component. Okay, now let's look at the third case. If you understand the first and the second case, the third case would be easier. So for the third case, let's say your surface is given as y as a function of x and z. Then the surface is either facing the positive side of y-axis or its negative side. So what you do is you check for the y component, which is your j. So you check that whether you want your j to be positive or negative. Then your normal vector is either del phi or negative del phi. Okay, let me explain that again in much more detail. Okay, now for example, example, let's say your surface is given as y is equal to x squared plus z squared. Again, this is going to be a paraboloid, like so. Say something like this. Okay. Then, as you can see, your paraboloid here is facing the negative y-axis. So the normal vector to the surface would be like so. Okay, it's pointing like that. Okay, as you can see, the y component is always negative because it's always to the left, but the x and the z component varies. Here the z component is positive, here the z component is negative, but the y component is always to the left, meaning that you want the j component to be negative. You want your j component to be negative because the surface is facing the negative y-axis. Okay, now let's rewrite our surface. Rewriting the surface as a function of x, y, and z. So if we rewrite this, you get y minus x squared minus z squared equals 0. Then the gradient of phi, differentiate phi with respect to x, you get negative 2x. Differentiate with respect to y, we get a 1. Differentiate with respect to z, we get negative 2z. Okay, now check the y component. The y component here is positive 1. But remember, we want our y component to be negative, which means that the normal vector is equal to negative del phi, which is equal to 2xi minus 1 plus 2z k. So that is the normal vector. Because you want the y component to be negative because the surface is facing the negative y-axis. Okay, another example is, let's say your surface is y equals negative x squared minus z squared. Okay, now if you plot this, this is also a paraboloid, but it's facing like so. Okay, it's also a paraboloid, a bowl shape, but it opens like so. Okay, now you can see that the surface is facing the positive y-axis, so the normal vector to the surface would be like so. Okay, it's always to the right, but then you can see that the x and the z component varies. It can be positive or negative, but the y component is always to the right, which is always positive, which means you want your j component to be positive. Okay, now rewriting our surface sigma as a function of x, y, and z. Now when you rewrite this, you get y plus x squared plus z squared. So the gradient of phi is equal to 2x. Differentiate phi with respect to y, you get a 1. Differentiate phi with respect to z, we get 2z. And then you check for the y component, and here the y component is already positive, the same sign as what we want. Then this is our normal vector. So normal vector is our del phi, which is equal to 2xi plus 1j plus 2zk. Okay, so that's how you determine which one is your normal vector. So your normal vector is either del phi or negative del phi, or the gradient of phi or negative gradient of phi. So it depends on where your surface sigma is facing. All right, so if it's z equals f of xy, you check for the z component, either it's facing upward or downward. If your surface is given as x as a function of y and z, you check for the x component. It can either be positive or negative. If your surface is given as y as a function of x and z, you check for the y component. The surface will either be facing the positive y-axis or negative y-axis. So you check for the y component. So that is your normal vector. It's either del phi or negative del phi. Okay, once you have that, then you can evaluate by using this. Okay, so then you can evaluate by using this formula, because then you know which one is your normal vector. So you just dot f and n first, project onto the plane, either xy plane, xz plane, or yz plane. Then it's back to double integral, and then evaluate as usual. For the example, I'm going to save that in our next video. Thank you.